Hello, complex analysis students. The topic for today is functions and mappings. So we're going to begin just by talking about functions. Now, in your foundations class, you've already learned the formal definition of a function. So you know this notation here means that f is a function with a domain of S and with a codomain of the complex numbers. And so that means that the range of this function is contained inside the complex numbers. So this is going to be a function that takes as input complex numbers from S and then gives output values in the complex numbers. And such functions are called complex valued functions. And so mainly we just need to get used to the idea and see some examples. And there are a few conventions that we need to talk about. So first of all, if someone gives you a function, maybe they just give you some formula for a function without specifying what the domain is, then the domain is always understood to be the largest subset of C on which that function is defined. We do this sort of thing with real valued functions all the time. Like if I give you the function, I say f of x equals square root of x, then you'll understand without me saying so that the domain of that function would be the set of x's where x is greater than or equal to 0. So we'll have similar considerations here in the complex plane. Usually we avoid dividing by 0 and things of that nature. And of course, in this book, he tends to call the domain of the function the domain of definition. You may remember in our previous section on topological terms, we had a word there for a subset of the complex plane called a domain. But there it wasn't talking about the domain of a function. It was just talking about an open set that is connected and that is non-empty. Of course, that'll have some connection to domains of complex functions a little later, but for now, let's just be sure that we distinguish the term domain of definition from the topological term domain that we talked about last time. So let's see a specific example here. So in this first example, we defined a function and we defined the domain of definition to be the complex numbers minus 0 and a codomain of the complex numbers. And the function is just f of z equals 1 over z. So you can see why we excluded 0 from the domain. And it's not unusual, I mean, most of the time, and I don't think our textbook uses this colon arrow notation at all for functions. Typically, people will just say something like, hey, w equals 1 over z. And if they don't state a definition, then it would be understood to be the largest possible subset of the complex plane on which that function is defined. And so if I just said w equals 1 over z, then you would know sort of implicitly the domain of definition would be c minus 0. Now with the same example, if we would set z equal to x plus iy like we normally do, then we could rewrite the function f of z equals 1 over z in a different form. We could write that as 1 over x plus iy, which we could sort of write in the standard form by multiplying by a conjugate. And when we do that, we'll end up with, so that would work out to x minus iy over x squared plus y squared, which we could then break into its real and imaginary parts. So x over x squared plus y squared plus, then we'd have negative y over x squared plus y squared multiplied times I. And when you do it this way, when you take your function and you put x plus iy in place of z and then you separate the function value into its real and imaginary parts, you get two functions. Typically, the real part we refer to as u of x comma y, and the imaginary part we call v of x comma y. You notice that these two the real part and the imaginary part are both functions of x and y. And in general, we can assume that a complex valued function can be written in the form u of x comma y plus I times v of x comma y, where u and v here are both real valued functions, because the real part and the imaginary part of a complex number are real numbers, right? Yeah, this is a convenient way to represent a complex valued function. That's sort of the rectangular form of the function values. We can also put it into exponential form or polar form, and we will do that a little later because sometimes functions are more easily understood or expressed in terms of polar coordinates or exponential form. For example, let's look at w equals z squared. Now here we're not stating a domain. The domain of definition for this function would naturally be all of the complex numbers. You can square any complex number, so that's your domain. So if we take z to be x plus iy, then our w function, that would be x plus iy squared. And so if you square that out, you get x squared, and then you get a minus y squared for the real part, plus then you get 2xy for your imaginary part. There's your real part, u of x comma y, and there's your imaginary part, v of x comma y. You could also put z into its sort of general exponential form, and then your w equals z squared function would become r e to the I theta quantity squared, and you'd get r squared e to the I times 2 theta. And so in kind of a similar way, you see that the radius part of the function can be expressed as a function of r and theta, and then likewise the exponent is a function of r and theta. We'll exploit this idea a little bit later. I think for this section though, we're mainly going to focus on rectangular form, but we may come back to polar form a little bit as we move along. The second part of this example that we just did, where we put things in a polar form, illustrates the next point I'm wanting to make, is that if you express z in exponential form in terms of r and theta, and then you can, in principle, break the function up into some u of r theta plus I times v r theta. So the real and imaginary part, indirectly, you can see that they depend on r and theta if you express z originally in terms of r and theta. Like going back to the z squared example a second ago, I didn't break it up here, but if I carried it a little bit further, this would be r squared, and then I'd have cosine of 2 theta plus I sine of 2 theta, which then you could write as r squared cosine of 2 theta, and there's your real part, plus I times r squared sine of 2 theta. So the r squared times sine of 2 theta is your imaginary part. And in general, you can do that. So let's do this for f of z equals 1 over z. Now we already have done f of z equals 1 over z in rectangular form. So here I want to express its real and imaginary parts in terms of r and theta. So this turns out to be pretty easy though. So if we say z is equal to r times e to the I theta, then from there, 1 over z, well, remember that would be 1 over r e to the I times negative theta. And of course, you can then, break that out into polar form. 1 over r cosine negative theta plus I times sine of negative theta. And then using negative angle identities, you can write this as 1 over r cosine of just theta, and then minus 1 over r sine of theta multiplied times I. So here, the 1 over r times cosine of theta is the real part, so that's u of r theta, the real part of f of z. And then likewise over here, this v of r theta, that's the imaginary part of f of z. So anyway, breaking up a function like this into its real imaginary parts, and whether you do it in terms of rectangular coordinates or whether you do it in terms of polar coordinates, you can do it either way, and whichever way is convenient for whatever task you're trying to accomplish at that moment. Sometimes one is easier than the other. So let's talk about some of the common types of functions that we see in complex variables. Well, first are polynomial functions. So polynomial functions are functions whose domains are the entire complex plane, and they look like this. They look like polynomials have always looked. The main thing you need to understand is that the coefficients can be complex numbers. So something like p of x equals 2z squared plus 1 minus I times z plus 4i would be a second degree polynomial. whatever if that a sub n is not 0, then you would say your polynomial is nth degree. So the one in red I did there was a second degree polynomial because that was just the coefficient of the highest degree term. And then, of course, we have rational functions like we've always had, and they're defined just as they always have been. They're just a rational function is just a polynomial divided by a polynomial. And those functions, their domain of definition is always just going to be all the values of z where the denominator function q of z is not equal to 0. So these functions make sense. And what we'd like to do eventually is get to where we have analogs of all the kinds of functions that you know about from, functions of real variables. Like you're aware of, like you've got trigonometric functions like sine and cosine. We'd like to have a sine of z and a cosine of z. But, right now, if I just wrote down cosine of z, I wouldn't have any way to make sense of it because the only way you've seen sine and cosine defined are in terms of a real parameter so far. So that would take some work to do. We'd like to have a logarithm of z and an exponential function of z. Right now, we don't even have a root function. Like, how about square root of z or something like that? So, but that we have enough information right now that we could make some sense out of it. So let's do root functions next. Okay, so one thing you need to remember is that when you see z to the 1 over n, that denotes the set of all the nth roots of z. And typically there are n of them unless you're talking about 0. So this is not a function. If I just write down, I couldn't write f of z equals z to the 1 over n if I wanted it to be a function. This would be a multi-valued function or a multifunction, but it's not what we usually consider a function. Functions always have the property that one input gives one output, but here we'd be getting one input gives multiple roots as outputs. So yeah, that wouldn't be a regular complex valued function. But what we could do is instead of considering all of the possible nth roots, we could just consider one of them. And the most common choice, if you're going to consider one of the roots, would be to consider the principal root. So how would that work? So if we take our z and we put it into polar form, or exponential form here, so if z is r e to the I theta, what is the principal root of that? Well, it would be, if you remember, it's the nth root of the radius, and then it's e to the I times theta over n. And here we have to be assuming that theta is the principal argument. So we get sort of a principal root function. And there we're just getting one value. So just as a concrete example, what would be the principal square root function? Well, if we're doing square roots, you would take the square root of your radius r, and then you'd have e to the I theta over 2, and here theta is the principal argument of z. Well, we have notation for that, capital ARG of z. So when we speak of mappings, it's sort of a way of thinking of how do we visualize what the function is doing. Like what kind of contortion is it performing on the complex plane? It's hard to visualize complex functions in the normal way because, if you have a real valued function, you can plot the input paired with the output and it's a two-dimensional point, right? But if you try to play the same game with complex functions, then the input is a complex number, but you can kind of think of a complex number as a two-dimensional point itself, and then you'd be pairing that with another two-dimensional point as the output. And then when you think about that pair of pairs, it's essentially a four-dimensional point. And we don't have visualizing four-dimensional points is kind of tricky. There are some ways of doing it, like there's projection methods and other things, but what would typically is done is to use a sort of before and after approach. So you've got this function, and the before set is just the domain. And what you usually do is, let's just say the domain is the whole complex plane, but it could be some portion of the complex plane. And then in that domain, you might look at some curves or some sort of grid in that domain, and you want to see what effect is the function having on that grid. So some typical sort of families of lines and curves you might use are like a square grid or maybe a polar grid. And then the after picture is just you look at what the effect is on those designated curves that you had in the domain. So let me give you a few examples of how this might go. Start with one that's really simple. On the left, that's your domain of the function z plus 2. And then I might pick a few curves, like some horizontal lines and some vertical lines. Like for example, here I picked y equals 3 as a horizontal line to consider and x equals 1 as a vertical line to consider. Now if I take all the points on those curves and I do z plus 2 on them, what effect does that have? Well, adding 2 is just going to have the effect of scooching those lines over horizontally to the right too. So you see that both of those lines in the after picture are just moved to the right too. Now that's apparent with the red line. The red line went from x equals 1 to x equals 3, but the green line, you can't really tell that it got moved over to, oh, there's a typo there. It should be y equals 3. But you can't see that any effect was had on that line y equals 3 because, we moved it horizontally, so it just fell on top of itself. Okay, here's an example. So maybe we can work together to figure out what's going on here. So the function is f of z equals I times z. So a very simple function. We're just taking the z and multiplying by I. So what effect does that have on, the plane? So I put a little patch up there in red and green. I want to focus on that grid in red and green and see what effect did the function have on that patch, that subset of the domain. Well, one thing that will really help you to understand this, the function w equals iz, if we replace z with, let me back up a little bit here. If I replace I with its exponential form, well, I is equal to e to the I pi over 2. And z, just the general variable, can be written as r e to the I theta. And then we could multiply this out, and what you end up with is r e to the I times theta plus pi over 2. What happened was that z, the original input, gets sent to, so z in the before picture gets sent to r e to the I theta plus pi over 2 in the after picture. And remember, z there was really just r e to the I theta. So what effect was had on z? Well, the difference is between the before and the after is that theta had pi over 2 added to it. So it seems to me that what's really going on here is rotation by pi over 2. And so if you applied a rotation of pi over 2 to that picture, here's what you get. So in the after picture there, you can see there was a rotation of pi over 2 that happened that took that region in the first quadrant to a region in the second quadrant. Notice that the vertical lines got transformed into horizontal lines and vice versa. Maybe let's look at a slightly more complicated function, but not a terribly complicated function. Let's look at the mapping w equals z squared. So there's a few ways that we could go about visualizing this in terms of before and after pictures. One way we'll do it in rectangular coordinates. If we're going to do things in rectangular coordinates, it makes sense to, like, what are the simple kind of curves that define rectangular coordinates? It would be horizontal and vertical lines, right? We could look at that. It would be easy to describe the sort of grid of horizontal and vertical lines. So just as a reminder, a little bit ago, for the function f of z equals z squared, in rectangular coordinates, we worked out that the real and imaginary parts are x squared minus y squared for the real part and 2xy for the imaginary part. I could look at a family of horizontal lines in the xy plane. So I want to think about this. I think you can see that a horizontal line, so the horizontal line that I'm thinking of would have the formula y equals c. So the horizontal line y equals c, you could express that in terms of complex numbers as z equals x plus I times c. So notice that the imaginary part there is just fixed to be c, in other words, the y-coordinate, but then the x-coordinate is just x, so it's a variable. And similarly, a vertical line, x equals d, that would be a vertical line sort of at the x value d. And you could express that in the complex plane with this formula. Z equals d plus iy. So this time, the real part is fixed to be d, and then the imaginary part is just y, so that's a variable, so the line goes up and down. So what I want to see is what happens if I just restrict to a horizontal line and I plug that into the function. What do I get as an output? So for horizontal lines being transformed, I would do f of x plus c times I. So here, all that's really going on is that, x is equal to x, but y is equal to c. And so I've already worked out the arithmetic in yellow above. So this would be x squared minus c squared plus 2 times x times c times I. So you've got a real part u equals x squared minus c squared, and you've got an imaginary part v equals 2 times c times x. Now if you look at that, that's really just a parametric way of describing a curve in the UV plane. So the UV plane is like your after plane. So the before plane is the xy plane, and then the after plane is the UV plane. This is just describing a curve here. Well, what curve is it describing? Well, we should be able to figure that out. If you took the second equation there and solve for x, you'd get x equals v over 2c. And then you could substitute that into the first equation, and you'd get u equals v squared over 4c squared minus c squared. So this equation describes a curve in the UV plane. U is usually your horizontal axis, and v is your vertical axis. So it's kind of like if you had a curve where you solve for x in terms of y in the xy plane. So when you graph it, it won't be like a function of u, it's a function of v. So it'll pass a horizontal line test, not a vertical line test. But in any event, we could graph that. I mean, if you put c equals 1 in there, you're going to get a parabola, right? You can tell, like if you put c equals 1 in there, you'd get u equals v squared over 4 minus 1. Well, I know from my algebra days that that's just a parabola. It'll be a sideways opening parabola. And we can do by translating the vertical lines, or transforming the vertical lines. So I would do f of d plus iy. So that just means that, I'm going to put d in place of x in that formula in yellow above, and y is just y. So I'd have d squared minus y squared plus 2 times d times y times I. So just like before, I've got u is equal to d squared minus y squared, and v is equal to 2 dy. So I could solve for y in the second equation and get v over 2d. I could substitute that into the first equation. I would get u equals d squared minus v squared over 4d squared. And if I would look at that equation there and think about different values of d that I could plug in, I again see parabolas. Like with d equal to 1, I get u equals 1 minus v squared over 4. So it's a parabola. So we're just getting a bunch of parabolas. So what I want to do is I just want to, in the before picture, plot a family of horizontal lines and vertical lines. So I'm going to pick various values of c and d and plot those horizontal and vertical lines. And then I want to see what the outputs would be if I plug those lines into the function. And I know I'm going to get some parabolas. So here's my family of horizontal and vertical lines. So in red, the horizontal lines, I've got them labeled by the various c values that they correspond to. And the same thing with the vertical lines correspond to specific values of d according to the formulas in blue and green right there toward the top. And so I know what to expect when I plug those into the z-squared function. I'm getting some parabolas. So, in this particular instance, I think what I will do is go to the computer and plot those families of parabolas on a separate graph and then copy it here into the picture. So let me do that. So after plotting the transformations of those red and green lines on the left, you can see what their corresponding outputs are. You'll notice that if you plug in c equals 1 or if you plug in c equals -1, you get the same result in this formula underlined in red up here at the top, because the c is being squared, so it doesn't matter whether you put plus or minus 1 in there. Same thing with plus and minus 2 and plus and minus 3. So you can tell that this function maps things in a 2-to-1 way. Two horizontal lines map onto each of these parabolas over on the right. And same thing with the vertical lines. You always have two vertical lines mapping to the green parabolas over there. The only exception to that is the x-axis. So anyway, so I don't know if that really gives me any huge insight as to how that function behaves, but I can see that it's warping the plane in some really sort of perverse way. It's not just warping it where straight things go to curvy things, but it does it in such a way that it maps in a 2-to-1 way. So maybe this is not the best visualization for this particular function, but it can give you some insight to how the function's behaving, depending on what you're looking for. An easier way to do it is actually to consider the polar exponential form. So remember, if we set z equal to re to the I theta, then z squared becomes r squared e to the I times 2 theta. The effect of this transformation, r e to the I theta, maps to r squared e to the 2I theta. It has these two separate effects. One, that the radius is stretching from r to r squared. So if r is between 0 and 1, you're getting this sort of compression effect, because if you square a number between 0 and 1, it gets smaller. And then it fixes things that have radius of equal to 1. So the unit circle, points on the unit circle, their radius don't change at all. And then points that have a radius bigger than 1 get sort of sent further away from the origin. And then the angle is doubling. So there's sort of a stretching and a rotation where whatever the angle of the input is, it gets doubled. So here's kind of a nice way to visualize that down here. So for my before picture, I want to focus on this little circular sector of radius 2 that goes between angle 0 and pi over 3. So just this little region right here. So if you take all the points in that region and you square their radii and you double their angle, it sends it to this region over here. And the red lines that I graphed in the before picture get sent to the red lines in the after picture. You can see that for those red lines, their angles doubled, right? And you can also see that, the points that were on that green circle of radius 1, the green line of radius 1 should have stayed where it was, so it should have been there. And then the green line of radius 2 got stretched out to the green line of the green curve of radius 4 on the after picture. So to me, that gives me a better sense of what that function is doing. It's doing this sort of like stretching and then doubling the angle at the same time. So it's easy to see what the effect of that is if you look at a circular sector. It just doubles the size of the pie, but also it doubles the angle of the pie, but it also sort of stretches out the radius of that piece of pie by the square of whatever its radius is. Moral of the story, though, is complex functions generally are not super easy to visualize. In some cases you can if they're pretty simple functions, and if they're very complicated at all, anything beyond basically the sort of things we've already been looking at, you usually need some sort of computer assist to help you visualize it, because you either have to do these complicated before and after pictures, and if there's a lot of curves in your before grid, then it's going to take a lot of effort to figure out what the after effect is on that grid, because there could be, like whatever, 20 or 30 different lines in your grid, so it'd be a lot of work. And there are other ways of visualizing them where you can think of the graph as a 4-dimensional thing, and then you can do a process called stereographic projection to sort of see a 3-dimensional shadow of it. But that requires certainly computer help, and there's also a lot of tinkering around with what's the right angle to project it out of 4 dimensions from, and so that can be kind of a tricky thing. But sometimes it's worth the effort if you're really trying to gain some insight on the behavior of the function. I guess I'll stop there. I think that's my last slide. Yeah. I'll stop there, and we'll talk to you again soon. Bye now.